All right. Good afternoon, everyone. Welcome to the class. In today's class, we're gonna finish the digital circuit chapter. And last time I said I will post the homework after the last Friday's class, but um, I will do that after today's class. And you all have 1 week to finish the homework. And at the last date of our class is at April 23rd, which is next Thursday. Okay, so we have four classes left. Um, for these four classes, I'm planning to use today's class to finish our last chapter and use uh, two classes to answer uh, questions like um, homework questions or any questions I find when I grade your exams or when I grade your homeworks. So I will summarize those questions and make two lectures to explain those questions. And for the last class, I will do the review for the final exam. Okay. Due to the situation, the special situation of this semester, we don't have face-to-face meeting, so the final exam gonna be take home, and just like exam two, I will post a final exam question on the campus, and you guys can download the exam questions, and after you guys finish the exam, scan it or take a photo of your solution and submit it or upload on the canvas so I can easily grade it. Okay. All right. So that's some plan. That's some plans for the remaining semester. And some people ask me about the homework extension. It's okay. If you need more time to finish your homework, it's definitely fine. But just make sure you submit all assignment you want to submit before the last day of the class. Okay. And do everything. Do the assignment ahead. Like don't wait until the last day and send me everything you are missing, and that will be a lot of work for both of us. Okay. All right. Without further talk, let's get started for today's lecture. At the beginning of today's lecture, I want to review the kernel map we mentioned in the last class, because I get some feedback about some confusions about the kernel map, and some people don't know what exactly we need the kernel map. What's the purpose of using kernel map, right? But actually, I explained the functionality or the purpose of kernel map in the last class. But I want to repeat. I want to repeat that. I want to repeat the purpose of the kernel map. So kernel map is a tool. It's a graphic tool for us to quickly simplify a logic expression. And this logic expression is not like the normal one. Something like f equals to a plus c, abc plus a b bar c bar, or a b bar c, something like this. But the logic expression is presented in a truth table or a SOP function. And I mentioned last time SOP stands for sum of product, and sum of product is just another representation of the truth table, right? Because truth table lists all combinations of input and the corresponding output of each possible combination of input, right? And the output of the truth table is either be 1 or 0. And a SOP function, let me show you a SOP function. I'm sorry. Let me show you a sample SOP function. A sample SOP function could be f a b c equals to sum of product, and inside this parentheses, we list all rows. Each row is representing a possible combination of inputs, right? We list all output that is 1, right? So such as 1, 2, 4, 5. And as long as you know these row numbers or these input combinations, you can deduce the entire truth table, right? Because the output is either be 1 or 0. So if you know all ones, then you can know all other inputs, as long as you know how many inputs we have, right? Because the number of inputs determines how many rows of the truth table, determines how many possible combinations we could have in a truth table. So let me explain the expression of the SOP function. In the SOP function, we write the number of inputs on the left side, right, inside the parentheses of a f function. And at the sum of product, sum of m means this logic expression is presented in the form of sum of product. Sum of product means just like this one. This is the sum of product logic expression. We have 3 terms, and each term is a logic product, and the final expression is the sum of logical products. So that's why we call it sum product, right? Very obvious. All right, so this function as sum of m is indicating that this function is a SOP function, right? And inside the parentheses list rows that output 1. Okay, each row, as I mentioned before, each row is representing a possible combination of input, right? This SOP function is equivalent to this truth table, and to explain this problem, I will show you the full truth table. Okay, but I will not do that in the latter lecture, because to draw a truth table is more complicated than giving a SOP function, especially when they have the same functionality. So drawing a complete truth table is unnecessary. Okay, all right. So in this truth table we have 3 inputs, and one critical question you need to ask yourself is, if you know you have 3 inputs, then how many possible ways, how many possible combinations you will have in the truth table, right? The way to calculate how many possible combinations is very simple. You just need to draw 3 blank lines, and on each line it could be 1 or 0, right? Or 0 or 1, one or the other. So in total we have 2 times 2 times 2 different possible combination, 2 different ways to combine these 3 different digits, right? So there will be 8 different combinations. In other words, we have 8 rows, and the order of listing these rows are following the increasing order. What that means? That means I will explain that later. Let me first finish the truth table. What that means? That means if you translate, or if you convert, or if you treat each row as an unsigned binary number. For instance, the first row is 0, 0, 0, and if you convert this unsigned binary number to the decimal number, that is 0 in the decimal number, right? and repeat this procedure for all rows, and we will have 0, 1, 2, 3, 4, 5, 6, 7, right? Correct. So that's actually is an increasing order for these rows. And the corresponding output, we can find this information in this part, right? So we know row 1, which is this row, the output is 1. Row 2, the output is 1. Row 4, the output is 1. Row 5, the output is 1. So after we know all rows that are outputting 1, then we can deduce, we can guess, we can estimate. Well, actually, we 100% confirm that all remaining rows are zeros, right? Like this. Okay? Alright, so that's the SOP function. And here, if you just from because in case you forget, but we do actually mention that in the previous class. We said there's a way to represent the truth table to a logic function, right? To a logic expression. That is called the synthesis of logic. The synthesis of logic expression, right? What that means? That means if you are given a truth table, then you can write the logic expression according to this truth table, and you can also draw the logic circuit implementation based on the logic expression, right? For instance, in this truth table, based on this truth table, we can write D actually equals to we have 3 steps to follow it, right? The first step is we focus on rows that are outputting 1. And if the input is 0, then we write the original input. If the input is 1, then we write the original input. If the input is 0, then we write the inverse of the input. So what that means? That means the first row is outputting 1, is row number 1, which is this guy, right? And the corresponding input is 0, 0, 1. So 0, the first 0 is representing we have the inverse of A, which means we need to write it as A bar. And then we have 0 for B, we need to write B bar, and we have 1 for C. That means we write C for the third input. Okay, so and then we multiply them together as a logic product, such as A bar, B bar, C. And the second row is outputting 1, is row number 2, which is this guy. So we have A bar, B, and C bar. Row number 4, A, B bar, C bar, plus row number 5, A, B bar, C, plus, and that's the last one, right? We only have 4 rows that are outputting 1, which means we only have 4 terms, 4 logic products in our logic expression. Right, so that's how we translate, or that's how we convert a truth table to a logic expression. And based on this logic expression, we can draw a logical circuit that is the implementation of this logic expression, right? But sometimes, if you have more than 4 rows that are outputting 1, for instance, if you have 6 rows that are outputting 1, then you have a longer logic expression. In other words, you have a larger or more complicated logic circuit. So some people may think about, can we have a tool, or can we have a way to simplify this logic expression before we try to implement this logic expression, right? And that is the answer. That is what kernel map does. That is what kernel map help us to simplify the logic expression. Okay, so also use this example, this SOP function. So if we use the kernel map tool, we first draw a blank kernel map, right? And we said on this part, on the up left corner, we write inputs, and we put 2 as a group, and the other one, because we only have 3 inputs here. If you have 4 input, then we write AB on one side, write CD on the other side. But since we only have 3, so you can write AB on one side and write C on the other side. Or what you can do is you write A on one side and write BC on the other side. It's the same thing, but you can just follow my way, because I think that may be easier, because that this representation has some common places with the 4 inputs kernel map, right? Because for 4 input kernel map, you just need to increase D here, right? But this is a 3 input, so we don't have to do that. Alright, then after we finish the input part, we write all possible combinations of input on the initial row and initial column of the kernel map. So for AB, we could have 4 possible inputs. They are 0, 0, 0, 1, 1, 1, and 1, 0. And as I mentioned last time, there's very important rule for writing those possible combinations of initial row and initial column, which is 2 consecutive rows. There's only 1 digit different, right? Based on this rule, in this column, we can only write 1, 1 instead of 1, 0. Because if you write 1, 0 here, then you compile these and these 2 columns. We have 2 different digits, and that is not allowed in the kernel map. Okay, and for C, that will be easy, because we only have 1 digit, so that will be 1 and 0. Alright, after that, we just need to fill the cell numbers in these blank cells. And as you can see, after you create this table or map, in other words, we have created 8 blank cells, right? If you count that, they are starting from 0, they are 0, 1, 2, 3, 4, 5, 6, and 7. 6 and 7. 8 different cells, right? And the way to label these cell numbers is exactly the way how we label these row numbers, right? We treat the input combination as an unsigned binary number, and we translate or convert this input combination to a decimal number, right? To a decimal number. And for instance, this cell inputs are 0, 0, 0. The corresponding decimal number is 0. And for this cell, the inputs are 0, 0, 1. The corresponding decimal is 1. And for this cell, for instance, the input is 1, 1, 1. The corresponding decimal number is 7, right? And then we just need to fill in row numbers that are outputting 1. For instance, we have row 1 is outputting 1, row 2 is outputting 1, row 3 is outputting 1. Row 3 is outputting 0, so we should not include that cell. And row 4, this guy, is outputting 1. Row 5, this guy is outputting 1, okay? After we fill these ones into the corresponding cells, the other cells are zeros, right? So you can ignore it. And the next step is very important step. We need to circle these ones in the way that inside of a circle there's only 2 to the power of n ones, and this n is an integer, right? So you could circle 2 to the power of 0 ones as a group, which means a single one as a group. Or you can circle 2 to the power of 1 of ones as a group. Or that means you can circle 2 ones in your group. Or 2 to the power of 2 ones in your group. That means 4 ones in your group. Or 2 to the power of 3 ones in your group. That means 8 ones in your group, right? So based on that rule, and also you can only circle consecutive ones in your circle, and diagonal ones are not allowed. What that means? That means, for instance, in this problem, we have cell 1 and cell 2. These two guys, some people may treat them as consecutive ones or neighborhood ones, but in fact they are not, because they are placed in a diagonal order, and that is not defined as consecutive or neighborhood ones in kernel map. Only vertical and horizontal ones are consecutive ones, and all boundaries are consecutive, or all boundaries are touched together. Okay. All right. So or adjacent. Yeah, that's the word I want to say. Adjacent or consecutive. Either way. All right. So for this problem, we have cell 4 and cell 5. These two very obvious. They are adjacent or consecutive ones. And a very common mistake is some people may circle this one as a single group, but in fact, after you treat this boundary and this boundary as adjacent, then cell 1 is adjacent with cell 5, right? And another very important role for the kernel map is overlap. Overlap circles are allowed. So you can do this. If you treat this as circle 1, this as circle 2, circle 1 is overlapping with circle 2, that is okay. Okay. All right, and the tricky one is cell number 2. Some people may say, well, is there a cell adjacent with cell number 2? The answer is no, right? It's just a single isolated one, right? So you can just circle cell number 2 as a single group, and that is allowed because a single one, the number of 1 could be 1, right? Could be a single one. So isolated or single one is can be circled as a single group, as a one group. Okay, all right. That's how we circle ones. And after this step, the final step is we need to translate these ones back to the logical product. So let's start from circle number 1. The way to translate a circle to the logical product is to find the unchanged variable. Okay, this sentence is very important. Let me repeat it. The way to change or the way to convert a circle back to the logical product is to find the unchanged variables. Okay, all right. So for instance, for circle number 1, we have AB is always equals to 1, 0. Why? Because circle 1 only occupies this column, and in this column, AB is always 1 and 0, right? And just as we mentioned earlier, if you have 1 for the input, then the logical product is the original input. If you have 0 in the input, then the logical product of that input is going to be the inverse of the input, which means we have B bar here. Okay, pretty easy, right? How about C? For C, do we have unchanged variable? Because C could be 0 or 1, and there's no unchanged variable, so that will be none. And combine these two together, these two rows together, we have AB bar as the output of the first column or of the first circle. Okay, talking about circle number 2, for AB, it occupies this guy and this guy, this column and this column, right? And if you check these two columns, you can easily find the unchanged variable is B, because B is always 0. B is 0, right? So we have B bar. A is changing. For this column, A is 1. For this column, A is 0, right? A is varying. So we only have B, and B is always 0. How about C? C is also unchanged. If you focus on cell number 2, C is always 1. C is always 1. So we have C as the original input, C. And combine these two guys together, we get B bar C. And for last guy 3, circle number 3, ABC is always 0, 1, 0, which means the logic product is A bar, B, and C bar, right? And finally, the final expiration, if you name it as D, that is the sum of these three logical products, and that will be A B bar plus B bar C plus A bar B C bar. Okay, and if you compile this result with the original expression, you will see a very obvious difference, and that is the number of terms, the number of logical products in these two logic expression. In the new logic expression, we only have 3 terms, but in the old one, we have 4 terms. So we have a simpler, or we have a more concise logic expression compounding to the original one. And what's more important is these two function, or these two logic expressions are equivalent. Okay, so they are representing the same logical circuit, or they are achieving the same functionality because they are sharing a same truth table. Okay. If you want to verify these two logic expressions, you can try to simplify this logic expression, and I believe you will end up with this logic, the new logic expression. And but the way we simplify the logic expression is using a graphical tool on the kernel map, which is simpler than the direct way to simplify this logic expression, right? All right. And let me see what else I want to mention. Oh, that's the last topic we have. So let's see one more example, and I will show you the. Let's do the homework question in the kernel map. Okay. Let me see if I have that information in my laptop, in my iPad. If I don't have, that's fine. I can quickly look it up, and write the question immediately. That's not a very hard problem. That's not a very long problem. Okay. So in your homework question, in problem number 4, where is my note? This one. In problem number 4, we have 2 sub-questions, which ask you to find the minimum of product expiration and draw the kernel map to simplify these 2 logic expressions. Oh, that's the wrong file. Should be. Where it is? Oh, here. Sorry, take some time to find the correct file. Yeah, this one. Alright, so in your homework, problem number 4. The first one is a 3 input. It's a 3 input SOP function, right? And I always remind you to prepare a blank kernel map in your notebook or on your cheat sheet, because that's very convenient to solve this type of questions. Or if you are very familiar with blank kernel map, you can memorize a blank kernel map and draw a blank kernel map at the beginning of this type of questions. Okay. So let me quickly draw a blank kernel map and let's try to solve this problem. Okay, so in this SOP function, we have 3 inputs, and this part lists all rows that are outputting ones. So in the corresponding position in the kernel map, we have row 0 is 1, row 1 is 1, row 2 is 1, row 4 is 1, row 7 is 1. Okay? Alright, so here we try to circle ones as groups, right? The very obvious combination is these vertical ones, right? These two vertical ones, we can circle them as a single group. And this guy, row 0 and cell 0 and cell 2 can form another group, right? And cell 4 and cell 0 can form another group because this boundary is adjacent with this boundary. Okay, and cell 7 is an isolated cell, so you just need to circle this guy alone, right? Or circle this one as a single cell. Alright, and then let's label these circles. This is circle number 1, this is circle number 2, circle number 3, and circle number 4. Right? So in the circle number 1, it occupies these two columns, right? So the unchanged variable is A is always 0, and C is always 0. So from these two information, we can write circle 1 as a logical product of A bar and C bar. B is changing, so we ignore it. For cell number 2, let me see what we have. We have A is varying, so it's not important because for this column A is 1, for this column A is 0, so A is varying. But B is always 0, and C is always 0, so we can write the logical product as B bar C bar. For cell number 3, we have AB is always 0 and C is changing, so we have A bar and B bar. And for cell number 4, we have ABC is 111, which means we have ABC for cell number 4. Okay? Alright. The final step is sum these 4 terms together to get the final expression, and that will be this term. F equals to that. Okay. Alright, so that's problem number 4. And the second question actually is the one that I want to present because this is a 4-input SOP function, and but it follows the same way to draw the kernel map, and it follows the same way to circle ones in the kernel map. Here we just need to increase another input on the upper left corner, and we list all possible combinations. I'm sorry, this should be 1 0 1. We list all possible combinations of input and here you will see a very obvious difference between 4 inputs kernel map and 3 inputs kernel map is we have more possible combinations in 4 inputs kernel map comparing to the 3 inputs one. Right? The way to label these cell numbers are the same that we used before. So for this cell, we have ABCD is 0001, and the corresponding decimal number is 0. The corresponding decimal number for this cell is 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So we have 16 different cells, right? And next, we just fill ones into the corresponding cells according to the SOP function. Cell 0 is 1, cell 1 is 1, cell 2 is 1, cell 3 is 1, 4 is 1, 9 is 1, 12 is 1, okay? And then we create circles. This vertical 4 ones can be circled as a single group, and these can be circled as a single group, right? And this guy 9 and 1 can be combined together as a single group. There's a not common mistake, but more like a point that some people will easily make problem is some people may also create a circle to circle 0 and 4 as a group. It's unnecessary because without this circle, you see, we already cover all ones with circles. So you don't need to repeat circles, right? You don't need to increase unnecessary circles because one circle is representing one logical product. The more circles you create in a kernel map, the more terms you will have in your final expression, and that will increase the complexity of the logic expression, and that will make the logic expression you find be the unsimplified logic expression, right? Alright, so let's find the corresponding logical product of these circles. So for circle number 1, AB is 0, 0, and the CD, you see, this circle occupies the entire column. And in this column, CD are varying. Right, CD sometimes are zeros and sometimes are ones, so they are varying. We can ignore that. But AB is always 0. So the corresponding logical product is A bar and B bar. For circle number 2, B is unchanged, right? Because B is always 0 and A is varying for circle number 2. But CD is always 0, 1. And combining that, we have B bar, C bar, D. For circle number 3, which is the last one, we have AB. For ABs, we only have B is unchanged variable, and that is always 1. And CD is always zeros, right? So combining them, we have B, C bar, and D bar. Alright, and the final step is we just need to sum that together to get the simplified logic expression, right? Just like that, easy. Alright, so that's the last topic in this lecture, in this chapter. And I may do the entire review for this chapter to help you guys to organize all logic or knowledge points of this chapter and help you guys to get a general picture of what we have learned in this chapter in the next class. And I will post the homework questions of this chapter after this class. And as usual, you have 1 week to finish the homework. Let me know if you have any questions regarding today's lecture or regarding the homeworks we have in the previous lectures. Okay? Alright, see you guys in the next class, and stay healthy.